Spectral lines are obtained when free-moving atoms of hot gas emits photons, or those of cold gas absorbs some of the incoming photons and lets the rest of them through. Let's cover some basic knowledge before we get to them. Light and the EM spectrum. Shown here is the known EM spectrum with increasing wavelength, therefore decreasing frequency, and photon energy as we move rightwards. This little part or range of wavelength, frequency, or energy here is the visible spectrum or light. Why visible? Well, that is because this is the only part of the EM spectrum that our eyes can detect and perceive. In increasing wavelength, VIBGYOR, that is violet, indigo, blue, green, yellow, orange, and red. Dark violet and dark red near the boundaries might be too dark to see, and hence many physics books consider the visible range to be from 400 nanometers to 700 nanometers. If we were to take the physics definition of color as that what is available in the visible spectrum of light waves, then black and white don't count as true physical colors. It's the absence of any of these true colors from violet to red results in no color being detected by the eye and therefore perceived black. And how about white? White is detected by the eye when the entire spectrum of visible light is available. What that means is that if photons from every wavelength from violet to red were to hit the eye at the same time, then the eye will perceive white. Which means white is not exactly a color, but the presence of every color in the visible part of the spectrum. If we compress or bring every possible photons between violet to red, then we get white. So, if you have white light or a mixture of photons from different wavelengths, then how would you split them up so that we could get out a spread of the constituent wavelengths and obtain this spectrum? That brings us to the next point. How to obtain a spectrum? Consider a stream of photons of a particular wavelength from the edge of the violet region and another wavelength from the edge of the red region radiated from a single light source. That would actually be a single beam of light emitted from a single source in the direction to the right containing that violet and red photons with their specific respective wavelengths. If you were to observe this beam on a screen, then it would be of the color pink, which is not from any part of the visible spectrum. To break them up and to observe the spectrum, that is the true component wavelengths, we can make use of certain properties of light, such as refraction, which is the bending of light when it travels from one optical medium to another of different optical densities. By placing a prism, in this case a triangular prism, the different wavelengths in the beam will undergo different levels of bending due to different refractive indices as it enters the prism at an angle to its boundary. With two instances of refraction at these two boundaries, the components are further spread out, and in this case you get two separate beams, the violet and the red, which you can then observe at distinct points on the screen. The stream of violet and red photons in the single beam from the source are deviated at different angles and made visible thanks to this prism. This is the path taken by the violet component, while this is the path of the red component. We have considered the violet and the red because they are the ends of the visible spectrum. If we know where they end up on the screen, then we could get out a pattern or trend on where the rest of the components would go if they were available from the source. And we will apply that now. Consider the source to emit pure white light. And you have learned that white light consists of the entire visible spectrum, that is from violet at about 350 nanometers to red at 750 nanometers. In increasing wavelength, the trend is VIBGYOR, that is violet, indigo, blue, green, yellow, orange, and red. Introducing the prism in the path of the white beam will split the light beam into its components by spreading them out like we have seen before, that is, with the violet being most deviated and red being the least deviated. That's the violet, that's the red, and the rest of the visible spectrum in the order of increasing wavelength will end up here, and you get VIBGYOR. What's obtained on this screen is called a spectrum. You can graduate the screen and put in a wavelength scale, a frequency scale, or an energy scale. And now we have a graduated screen that we can then use to detect the wavelengths, frequencies, or energies of the various components of the spectral output from an incoming beam. Let's upgrade the source to one that emits the entire spectrum, the visible and the invisible parts. Consider a white star which emits the entire EM spectrum. A source that emits the entire EM spectrum will be perceived as white. This is because wavelengths beyond red and below violet are invisible, and the resultant color from violet to red is seen as white. We have seen where violet to red will be on the screen. The wavelengths lower than violet are invisible to the eye and will end up at this region, while the wavelengths higher than red are too invisible to the eye and will end up at this region. This setup can then be used to find the components of the incoming beam, therefore the nature of the source. Emission spectra. Before we define emission spectra, let's look at the situation that results in one. Consider a hot gas cloud made up of atoms of a single hypothetical element named Q, which has 3 distinct energy levels. And here is one of its atoms, its positively charged nucleus and orbiting electrons in its 3 energy levels with their potentials shown increasing with radius. The word hot implies that its electrons are at higher energy levels, which means that they are vacancies at lower energy levels. And whenever such vacancies are made available, an electron from a higher energy level will fall into it to achieve stability, thereby losing its potential energy. And based on the principle of conservation of energy, that loss in potential energy will be given off as a single photon of a unique wavelength. In our hypothetical atom, 3 energy levels are available, and we are looking for every possible electron transition that could result in the generation of a photon. An electron could fall from the third to the first, that is from a potential of negative 10.96 electron volts to negative 13.60 electron volts. The difference 2.64 electron volts, resulting in a photon of energy 2.64 electron volts, which corresponds to 470 nanometer wavelength, which is in the blue region. An electron could fall from the third to the second, that is from the potential of negative 10.96 electron volts to negative 11.75 electron volts, generating a 0.79 electron volt photon, which is 1570 nanometer in the infrared region. And finally, you could have the same electron or any other electron from the second to the first, generating a photon of energy 1.85 electron volts corresponding to a wavelength of 670 nanometers, which is in the red region. With so many atoms in the gas cloud and in constant random motion, these 3 wavelengths could be emitted in any direction. By putting a slit, an aperture, we can obtain a narrow beam of light containing these 3 wavelengths from this gas cloud, focus it and pass it through a prism or a diffraction grating. The prism will disperse the constituent wavelengths in varying angles, thereby splitting them up into 3 separate beams. And the graduated screen, which was initially black, will light up or glow at 3 possible locations, each corresponding to the wavelength of the incoming photon. In total, 3 transitions are available. Therefore, 3 distinct photons, implying 3 distinct wavelengths, could be emitted, of which 2 are in the visible range, thus 2 colored lines on a screen with a black background. This is the emission spectra, and this part will constitute the visible emission spectra. Let's define. An emission line spectrum consists of a series of separate bright lines of definite wavelengths on a dark background produced by electron transitions within individual atoms of vapors or gases at low pressure as the electrons fall from higher energy level to lower energy levels. If you are able to observe the detected colored lines, obviously, and the invisible lines by other means, you can find out how many energy levels are there in the gas atoms, and at what wavelengths or potential energy differences those energy levels are in. And remember, the energies of the detected photon equals the difference in the energy levels, not the energy levels themselves. And you would have learned in chemistry that no 2 elements have the same energy level diagram, which means this spectral output is a signature of this element. Another point to note is that with energy given off in the form of photons, that is radiation basically, the gas eventually cools down. Next, absorption spectra. Before we get to defining what an absorption spectra is, let's look at the situation that results in one. Consider this time a cold gas cloud made up of atoms of the same hypothetical element named Q with the same 3 distinct energy levels of increasing potential. And here is one of its atoms, its nucleus and electrons in its 3 energy levels with their potentials. The word cool implies that its electrons are at lower energy levels, which means that there are vacancies at higher energy levels. This cold gas would not be emitting any radiation, no photons emitted. Therefore, when we observe this cold gas cloud through a prism, we obtain a black screen. Let's change that. To this setup, in a direct line of sight to the prism, we introduce the white star, which contains every wavelength in the EM spectrum. It is obviously perceived white because it emits the entire visible spectrum as well. With the entire range of photons, in other words, the entire range of wavelengths available with varying photon energies in this single beam and shot through the cold gas cloud, those with photon energies equal to the available differences between any two energy levels will get absorbed by the electron at the low energy level to get to a higher energy level. And the rest of the unabsorbed photons will continue on in its straight line journey. Consider an electron in the lowest energy level at a potential of negative 13.6 electron volts. It could jump to the second energy level, which has a potential of negative 11.75 electron volts, by absorbing a photon of that difference in potential energy, that is a 1.85 electron volts. And a photon of energy 1.85 electron volts, corresponding to a wavelength of 670 nanometers, is indeed available. It is within the range of that available in white light in the red region. Similarly, an electron could jump from the second to the third by absorbing a photon of energy 0.79 electron volts corresponding to 1570 nanometer wavelength in the infrared region. An electron could also jump from the first to the third directly by absorbing a photon of energy 2.64 electron volts corresponding to 470 nanometers wavelength available in white light in the blue region. Therefore, an electron from a lower energy level can jump to a high energy level by absorbing a single quanta or photon, and if that photon with the right photon energy, thus wavelength, thus frequency is available, then that gets absorbed. The rest of the photons will pass through the cloud, through the prism, and onto the screen. The prism will disperse the constituent wavelengths in varying angles, thereby splitting them up and forming a spectrum with 3 gaps or 3 missing wavelengths corresponding to the 3 wavelengths that were absorbed. In our hypothetical atom Q, 3 energy levels are available, and we are looking for every possible electron transition that could take place as a result of absorbing a specific photon, in this case called a characteristic photon. In total, 3 transitions are available. Therefore, 3 distinct photons implying 3 distinct wavelengths could be absorbed, thus 3 missing lines on the screen with a colored background. 2 of those missing lines will be obviously visible as they fall within the visible spectra. The third one is in the infrared region and therefore not visibly detected as missing, although it is. This is the absorption spectra, and this part would be the visible absorption spectra. Let's define. An absorption line spectrum is a continuous spectrum crossed by dark lines due to some missing frequencies. This is produced when a continuous spectrum of white light passes through a cold vapor or gas, such that absorption of photons of various characteristic frequencies by the atoms take place and the rest is let to pass through to result in this spectrum, which then validates that this spectral output is the spectral signature of this element. Finally, emission and absorption spectra form a single system. Let's put everything we have learned into a single scenario. Consider a white star that emits the entire EM range. If you were to directly observe this star using a slit and a prism, you would get the entire spectrum, the visible and the invisible parts, and this is the emission spectrum of the star, which is the source. If you let this star shine a beam of its spectrum onto a gas cloud and then observe the output through another slit and a prism in a direct line of sight, then you would obtain another spectra with missing wavelengths, which corresponds to energies absorbed by electrons transitioning to a higher energy level. This would be absorption spectra of the gas cloud. And if you observe this gas cloud through a slit and a prism at any other angles not in a direct line of sight to the source, then you would obtain an emission spectra. Now, listen carefully. This is because the electrons in the cold gas cloud, which had absorbed incoming photons and moved to a higher energy level, may fall back to a lower energy level and release a photon or a series of photons corresponding to their loss in potential. And these photons are emitted in random directions. A sample of these photons can be made to fall onto the screen, thereby generating the emission spectrum of the same gas cloud.